Hi guys, what's the crack? How we doing? Hi Kitan, hi Priscilla. Well, kind of just before I answer the question, in case you can't hear me, can you give me like a yes if we're good? If you hear me fine, hopefully you can. Yes, are we good? Help. I see 555 or Kitan. No? We can hear me? Not hear me? Yes, can. Thank you, Priscilla. Thank you. I honestly had a little bit of panic there. I was like, oh, which microphone am I supposed to be on? Thank you. Yeah, I see 555. What's your name? But yeah, we're gonna hopefully get to the end. Did you get the right answer? I put the answer up the last day. YouTube. Is it Esra? The school that I taught at, we blocked YouTube. So it kind of depends on your school. So no, my school didn't let you get onto YouTube. Only teachers could. So I guess it depends on your school rules, really, more than anything. The answer, so I can give you the answer just so you can see if you got it right or not. The answer was 5.58 grams. I see 555. So it was 5.58 grams. Did you get that? Ah, Timothy, you finally got to the right lesson, eh? Carla, hello. Omar, no worries. I'm glad you came for this one. 5.56 times 10 to the power of 3 kilograms. You got the right number. Did you mean to write positive 3 there or negative 3? Because we got negative 3 kilograms, I see 555. You're perfect. But if you got a positive 3 for kilograms, you're not perfect. So it depends if you got a positive 3 or a negative 3. But you've got the right magnitude. So that, yeah, negative. Happy days. Good job. You're good. Okay, so it's 2 o'clock. We'll get started. Yes. Yes. Kitchen, yeah, that's what I see 555 was just asking about. So hope if we get through today's lesson, like see how you guys find it, then we'll drop it in at the end, sure. So just in case anyone's new, again, a bit about me. So you know I just loved science, still do. um, Mostly interested in astrobiology now more than anything. But yeah, so I did astrophysics at university, and I'm pretty sure it's the same people, so I don't want to bore you with me again. But yes, I've been teaching for a few years. I've been head of physics at a couple of schools in London. So I don't know if you know, like Elephant and Castle. I was there in Hounslow, and then down Surrey or Epsom. Okay, so just to see if we are good for last day, can you try question one, pop in the chat? So remember we said that AQA, I know some of your different exam boards, but if you learn the AQA definitions, you'll definitely not lose mark in the other exam boards because AQA is the harshest one with exact definitions because they've printed them out, they've given the definitions in the textbooks for you guys, just expect you to learn them, right? Ah, right, you're from Hounslow. What school? Maybe what was it called? Park. I was at PARK. Some of the random distribution of kinetic and potential energies. Kitan. Yes. Good job. Yeah. So we're just going to, if you can read Kitan's answer, that's perfect. So internal energy is the sum of, so remember I say sum of, and it's nice that he put in there the random. So remember we said it was like kind of like a Boltzmann curve last lesson, where it's distribution of energies. Some of the random distribution of kinetic energies, but you're going to write the full word, and potential energies. Yeah, internal energy. Yeah, so internal energy. I see 555. That's like the GCSE definition. So you just have to make sure you've written what Kitan said there just above you in the chat for your AQA definition. Yeah. Well, Park's not Hounslow. Well, Garrick was the kid. Where's Park then? I thought it was Hounslow. Near Gatwick Airport. Am I completely off? Gosh, I think if I drove there for a year, I know where it was. IB physics. IB. Is that the international physics? Yeah, next one, lovely. I made a stupid mistake last time, right? So we have to add 273, which is perfect. So we get 283 Kelvin, because we remember our units always want to be in Kelvin. Remember, we use Kelvin because Kelvin is our value for absolute zero. Yeah, for international physics, 100%, yes. So like we were saying last time, all AQA, OCR, the international physics systems, they all need to know the same stuff, the same general stuff. The only difference is where they put them on your papers. So the international physics, you guys have to know slightly less. So we might be going a bit more in depth than you need to know, but you're not going to be at a disadvantage. So it's not that you need to know stuff I'm not going to teach you. It's more that you just need to know a little bit less. But at the same time, if you want to go to university, hopefully do physics, right? You still need to know the same stuff that everyone else knew coming from AQA or OCR. Kitan, just go right there because yeah, perfect, brilliant. So Pacific heat capacity is exactly, Kitan, you're on it today, thank you. Pacific heat capacity is the amount of energy required to change the temperature of 1 kilogram substance by 1 Kelvin without a change in state. That's perfect. Nice. So we just read what Kitan wrote there. So again, the amount of energy to change 1 kilogram of substance by 1 Kelvin, because remember we're in AQA now, we're in upper school, not degrees Celsius. 1 kilogram, 1 Kelvin without change in state. Without a change in state. Okay, so I'll answer some of the questions in the chat. Can everyone have this one to go? So I'm just going to draw a picture and I'll get your questions. So remember, pictures help out. So I got a bucket. We did this last day. My bucket is filled with 0.7 kilograms of water at 25 degrees. And then it says we're dropping 11 grams of ice. So hopefully straight away you're thinking that's 0.011 kilograms of ice. It's initially at -5, okay? So think about what does the ice have to do first when it's dropped in the water? Then once the ice is dropped in the water and it goes to some certain number, we're thinking about a certain number. AO, yeah, it's 1 kilogram. Remember, masses in physics is always kilograms. It's just chemistry, you always talk about grams. So give this one a go, see if you can get the answer. So just if you don't want to look at your data sheet there, E equals ml is what we're using for a change in state, and E equals mc, change in temperature, for when there's a change in temperature. So there's your two equations, and here is the data that you need. The hint is you should need to use all the data they give you in the question, so hopefully that'll help you out. So have a go at it. 4,700. You think that's the final temperature reached by the water? So like you kind of, is that what you said, Druka? I'm not sure. So the water starts at 25, right? We're putting -5 ice in. Yeah, I was going to say, it can't just shoot up to 4,700. Yeah. Someone asked me there about astro. So summer school, I'm not teaching astrophysics. So we're not doing that. But if you hopefully join the course through the year, right? So through the year, remember we said I'll be teaching the course, the full course. So like if you didn't go to school and you just went to my lessons, which I don't recommend because school's good for you. School's obviously good. And your teachers obviously know what they're doing. They wouldn't be your teachers, right? But like say you didn't for some reason and you only came to my classes, yeah, you'd cover the full spec, right? And then we're doing one section of astro. So if you're doing AQA, there's an optional topic. So it's either astro or you might do further mechanics. And I'm not 100% sure yet how we're going to do it exactly, but there only is 8 lessons where we're covering astro. So think about it, there's going to be, I think there's 80 lessons in total for the whole year. There only is 8 lessons where we're covering astro, and I'm going to see maybe if the other guy who teaches physics here, he's called Dario, if he might be able to do a different topic in those 8 lessons. But again, that's the only unsure bit. The sure bit is we're only covering 8 lessons on it. So it's not like you join the course, you're at a big disadvantage. It's only 8 lessons. Oh, sorry, Isra. Yes, the very last lesson. Yeah, so I guess if you're not doing astro, but again, it's quite interesting, right? I think astrophysics is really interesting. Yeah, Drika, your teacher picks the one they like the best, right? It's kind of annoying for you guys, but at the same time, yeah, they pick what they like. But they all are quite similar. So if you're doing medical and astro both have a big topic on lenses. So again, there's quite overlap between them, but the main body is quite different, I guess. It's right, yeah, 100% I would. Like 100%. And in interviews, I would talk about it. So they're always going to ask, like, what are you doing to get ahead? How are you reaching your contacts? So again, like, yeah, summer school is a really good thing, right? So I all went to summer school. I was helping people out on the chat. I helped them answer questions. yeah, stuff like that is great. Okay, 23.3 is what I'm saying. Happy days. Carla, you're a star. Yes. Timothy, you're a star. Yes, good on you. Brilliant. Well, Drika, then if you want to do Astro at school, like I said, it's only 8 lessons for the whole of next year out of the 80 that we're doing Astro. So if you just join them, at least that will have you covered everything that you want to do for Astro. So for example, say you apply for Astrophysics, Drika, and they say to you, oh, but you didn't do that topic in school. You could say, oh yeah, but I attended the My Spades course and I learned all the content there. Do you know what I mean? So you're telling them that you have learned the content, and you're showing them what you did extra to kind of get you ahead to get into uni. So that'd be quite a good thing to talk about if you're thinking about it for uni. Okay, so just to make sure we're good then, it sounds 23 is perfect. Hi, beautiful. Yes. Okay, so what we're thinking is the first thing I know is I have to remember the number 0 degrees C, right? Because water changes state at 0 degrees Celsius. So what I'm going to do then is I have to remember, first thing that has to happen is my mass of ice, and the specific heat capacity of ice is 2,100, has to increase in temperature by 5 Celsius to get to 0. So when I do that math, and I did it a second ago, you get 115.5 joules. The next thing that has to happen is my ice at 0 degrees Celsius has to change state to water at 0 degrees Celsius, right? So that's my change in state. So I take my mass, which is 0.011, times the specific latent heat of fusion, because it's a change in state from a solid to a liquid. And you should have got a final answer there when I did it of 3696. And then, now that we have water at 0 degrees Celsius, it's now inside our other water at 25 degrees Celsius. So these two waters now, they need to become in equilibrium with each other. So because they need to come in equilibrium with each other, we know that this water has to lower in temperature. So that E equals the mass of water there, which is 0.7, times the specific heat capacity of water, times that change in temperature. And this is the trick bit, right? We can't write final minus initial here because that will give me a negative number overall because we know it's going to lower. Because remember that number in there, the temperature change is a magnitude. It has to be positive. So you have to be careful that in that box you write 25 minus whatever temperature is its equilibrium, right? And then we just said our water at 0 degrees Celsius also has to get to that equilibrium. So we had 0.011 grams of water. That has to also increase in temperature from the 0 to its final temperature. So remember, when you take away 0, it just becomes that final temperature. And then we just need to equate these, right? So if I simplify this first, if I simplify this bit that I did earlier, you get 46.2 times T. And if you simplify this bit that I did earlier, you get 73500 minus 2940T. Okay? So now what we do is we have to equate the energy losses to the energy gains. Okay, so I'm just going to change colors here so you can see my final writing so you can follow along. So we're going to say 115.5 plus 3696 plus 26.2 T has to equal, sorry, it's not very clear, that's 26.2, has to equal 73500 minus 2940 T. And then all you need to do is take your numbers of the same size, right? So what I would do is I would take the negative over here to become a positive, and then take your numbers over here to become negative. So then what you'll get left with is 2986.2 times T is equal to 69688.5. So you get T, divide both sides with the same number to get 23.3 degrees Celsius. So exactly like a few of you said there a minute ago. So awesome. Yeah, I see 555, beautiful. So these are their specific heat capacity equations. So it's when you do thermal physics. So we're in the topic of thermal physics right now. Thermal physics. So thermal physics. So it's all about reaching, it's the first law of thermodynamics. So things that are in contact, they'll become in equilibrium temperature with each other. Yeah. Yes, that's great. You guys, nice. Oh, speaking of, is that what helped you out? Did you all do the homework? Actually, I can tell you all did the homework. Like 48, 29 you did the homework, which was great. So was the homework good, not good? It seemed that everyone did, right? I saw Anna, Sean's, Yusuf, Kai, Jack. They all looked pretty good, right? And it seemed that everyone passed it. So did you watch the video solutions? Did they help out? Or how did you find the video solutions? Tell me you liked it. I see 555, you like problem solving? Yep. Just silly mistakes. How did a 46.2t turn to 20? How did the 46? Oh no, that's just me. That's just, did I write that down wrong? 46.2t. Oh yeah, sorry. No, you're 100% right. Thank you for, yeah, duh. I don't know where I got that 2 from. I can't read my own writing. Sorry. 46.2. I apologize. Thank you for pointing that out. Yeah. The math is right. I just must have wrote that number down there wrong. So yeah, it is at 46.2. So if you follow the math through there as I've written it on that page, that is right. I think, I don't know. I must have been saying the number 2 as I was writing it. More question from homework. Yeah, so Timmy, sorry, I'm giving you a nickname. I don't even know you, sorry. Timothy. Through the whole year, so the summer school, just because it's summer school and we didn't want to overwhelm you guys with homework, we just want to let you know how homework would be. So summer school is just 3 multiple choice questions and then the solutions and the video solutions. But through the year, you'll get 10 written questions after every lesson, and then you'll have the video solution to mark it. So yeah, so there is more. And it's good you're asking more. There is more through the year. So through the year, instead of it being 3 multiple choice, it'll be 10 written questions after every lesson. Yeah, hopefully that answers Kitan's question there too. Okay, so moving on to our gas laws then today. So first one says, what is the pressure of a gas and how is pressure related to volume? So I'm not sure if some of you have done this already in year 12. So like I said last time, I teach this topic in year 12 just to give you a head start getting in year 13. But I know some teachers hold back a little bit. So what do you think? How is pressure of a gas related to volume? How would you describe it? Force per unit area? Yeah, perfect. So pressure per gas, we all know from like key stage 3, right? Pressure is force divided by area. Okay, so if we look here, this shows you the gas before compression and the gas after compression. So I can see here, I've decreased the volume, I've dropped the volume, and what you can see has happened to the pressure. Pressure is force to the container per unit area. Yes, nice. They're inversely proportional. Yes, perfect. Oh, Gary, 100%. I misspoke. Yes, sorry. It's 10 every month. You have 10 written questions. Every lesson you have 5 written questions. I apologize. Thank you, Gary. Yeah, nice, good job. So the vocab here again, like we just said, AQA is really hot on the vocab, right? So what we can see here, if the volume drops, okay, let's say I'm a single particle in here. If the volume drops, look at my 2 green particles, this particle has a big distance to travel before it hits the wall of the container, whereas this particle has a smaller distance to travel before it hits the wall of the container. So we know speed equals distance divided by time, right? So if my particles here, they're both traveling at the same speed, right? Because I've not changed the temperature at all. The temperature's staying the same. So they've not changed the speed. The speed is the same of both particles. So let's say they both got speed S. But the particle in the top piston has a larger distance to travel. So that means there'll be a longer time before it hits this wall. Whereas in the particle down in my blue box, because the distance there is much shorter, the time before it hits the wall is much less. So we can see the time between the collisions is less when we decrease the volume. Okay, so that's the first thing you always have to talk about. Time between collisions is less when we decrease the volume. Now everyone talked about how pressure is force divided by area, okay? But you have to always talk about momentum in these questions. Does anyone know how to get this into momentum? I see 555, that's super close. So instead of talking about, I want to say force is equal to, how can we relate force to momentum? So like someone said before, we're always going to talk about unit area. So if we talk about unit area, it's kind of like saying area is 1. So basically just saying pressure and force are the same thing. If force goes up, pressure goes up. If force goes down, pressure goes down. Yeah, so the rate of change momentum. Yeah, good job. So force is the rate of change momentum, which means we put it over time. Thank you, IC555. And then just in case you didn't know where that came from, we know F equals ma, mass times acceleration. I know acceleration is the change in velocity over time, or you can write that as final velocity minus initial velocity over time. So now I just sub that in there. So I've got force is mass upon V minus U over T, which is mass upon V minus mass upon U all over T. So you can clearly see that force is the change in the momentum over time. So this is the equation that you always need to talk about when you talk about the gas laws. Okay, so they're not going to be happy with any of your answers in these questions if you don't talk about change momentum. Okay, so we go back to what we talked about just a second ago. So what we said was, if there is the time between collisions is much less, so the time between the collisions is much less, I have decreased this value of t. Okay, and you can clearly see if the bottom number decreases, what that means is my force is going to increase. So what we've just done is explain why when the volume drops, because there's less time between collisions, that means the force will increase. And we know because we talk about unit area, that means the pressure is going to increase. Okay, so just to see that again. So what we're saying again, so the pressure exerted by a gas is inversely proportional to the volume. Okay, because we said as the volume drops, the time between collisions decreases, so the force increases. So the pressure increases because force is pressure per unit area. So again, like we said at the very start, and I can't remember, some of them are popped in the chat, volume and pressure are inversely proportional. So that's how we write when something is inversely proportional, either one of these ways. So what that means is it's equal to some constant over the pressure. So volume is equal to some constant over the pressure, or you can write it as pressure equals some constant over the volume. It's just the same thing. And that's why we get a graph that looks like this, because they're inversely proportional. Okay? So P times V is equal to constant. That's where that came from. If we multiply both sides by V, PV equals some constant K. Okay, so it's your first gas law. This gas law is called Boyle's law. Okay? You'll bear with me, but this is how I remember it. And honestly, it's the only way that I can remember it, and it's helped out my other classes, so hopefully it helps you guys out. There's 3 laws: Boyle's, Charles, and pressure. Okay? And you have to remember which one is which. So how I remember it is Boyle's law. You think about boiling, right? And if anything is boiling, you know that's got to do with a change in temperature. Okay? But it's spelt wrong. It's not actually spelt boiling. So because it's spelt wrong, it's got nothing to do with temperature. So it has to do with pressure and volume. Okay? And I'll tell you that again when we go for the other ones. But again, Boyle's law, you think about boiling, you think about a change in temperature, but it's spelt wrong. So it can't be anything to do with temperature. So it must be to do with pressure and volume. Okay? So Boyle's law is to do with pressure and volume, that they're inversely proportional. Okay, what about this one? How are volume and temperature related? How are volume and temperature related? So again, I've got pictures down here. So you can clearly see as we heat it up and we increase the temperature. Yeah, Draga, it is. This topic is a lot more rote learning than anything. But those, I'm going to show you some exam questions at the end, but it does come up often. It's describe Boyle's law, explain Boyle's law, explain Charles' law. And they are, once you do past papers, like I'm sure you've done loads of past papers from paper 1 already. Once you do loads of past papers, paper 2, they need the same vocab year after year. So they are really specific with it. Lower the volume, lower the temperature. Lower the volume, lower the temperature. Yeah, nice. So that means they're directly proportional, right? So we just said that. So volume and temperature. Remember we said they always want us to talk about momentum. Can anyone get some words in there to do with momentum? Omar, directly proportional is nice. So, Drega, stay with us. We're away from the pressure now. We're just talking about volume and temperature. So as I increase the temperature, can anyone relate that to momentum and why that would affect the volume? So if we're only looking, remember about GCSE, IV, CV, DV. We can only change one thing each time, right? So that means our pressure has to stay constant. So our pressure has to stay constant. Increase momentum. Yes, good job, right? So if I increase the temperature, what you have to say here is that the mean kinetic energy increases. Okay? So you can't write kinetic energy increases. I'm stressing this again. You have to write mean. Okay? Because remember we talked about that Boltzmann curve. You can't just say that the kinetic energy increases. It's the mean, the average of all of those particles' energies. Because maybe they've got a distribution of energies. So that's why they want to make sure that you know that and you write mean. Not that you're saying all particles increase in kinetic energy because they all have the same kinetic energy. They don't. They have a range of kinetic energies and the mean increases. Yeah? So as we increase temperature, the mean kinetic energy increases. So because we know, because we know that momentum is mass times velocity, if I increase the kinetic energy of them all, I'm increasing the speed of them all. So we know there's going to be a bigger change in momentum, okay? And then we also know force is change in momentum over time. okay? So what we said here is we want the pressure to stay the same, don't we? So we said, remember, we said pressure is force divided by area. When we talk about a unit area, we can just say pressure and force are the same thing. So we need force to stay the same. So if our change momentum has got higher, the only way for force to stay the same is for our time between collisions to also increase. And the only way for time between collisions to increase is if they have a greater distance to travel. And the only way to get them a bigger distance to travel means that we need a greater volume. Okay, so we're going to talk about that one more time. So we just said, if I increase the temperature, we have to say the mean kinetic energy increases. The mean kinetic energy increases, we know there's a bigger change momentum. But because the pressure has to stay the same, that means the force has to stay the same. So the only way to get the force the same if the momentum increases is to make a bigger time. So we need a bigger time between collisions. And the only way to get a bigger time before these particles collide with the walls of the container is to increase the distance they have to travel before they hit that wall. Okay, so you can kind of see it's the similar type of vocab all the time. You just have to talk about change momentum. Okay, and this one is Charles' law. Okay, so remember Boyle's law sounds like boiling, but it's spelt wrong, so it's nothing to do with temperature, so it's pressure and volume. So Charles' law must be to do with temperature, and it's temperature and volume. And they said they're directly proportional. That's what we just proved. And if something is directly proportional, we write it like this, or I can write it as some constant times T. Okay. Key thing to stress here, it's directly proportional to temperature in Kelvin. Remember, we stress Kelvin all the time. Because you learned in GCSEs, a directly proportional relationship goes for the origin, a straight line for the origin. The only way for this one to pass 0, 0 is if we use Kelvin. If you use degrees Celsius, it will not pass 0, 0. What number, can you pop in the chat, what number would it pass the origin at if I put volume against temperature in Celsius? So there's 0 Celsius there. Where is it going to cross the y-axis? Yeah, thank you, here. Yeah, nice. So I'd find negative 273, and then that's where it would cross the axis. Okay, so remember that we only say they're directly proportional if we talk about Kelvin. Yeah, loads of negative 273. Yeah, perfect, great. Okay, so one more law to do is pressure law. Okay, so we said pressure must be due with temperature as well. Pressure law must be due with pressure. It's called the pressure law. So it's pressure and temperature. So can you try and do the whole thing now? So how are pressure and temperature related? And can you get that into the words with momentum? So give it a go. How are pressure and temperature related? And can you get words in there to do with momentum? So remember, if we're talking about pressure and temperature, the volume is constant. So how are pressure and temperature related? Can you get in the words momentum? Give your answer, go there in the chat. How would you write it? So we're thinking as temperature increases, what's going to happen? Yeah, good job. So a higher temperature, something, we're going to say the change in momentum increases. Nice. As temperature increases, pressure increases, higher mean kinetic energy. Thank you, IC55. That's what we need here. So we're going to have an increase in the mean kinetic energy. And then we can add in what Carl said there. There will be a bigger change in momentum. Good job. Because the speed must increase if kinetic energy increases. Good job. So then now, if we've got this part, which is all perfect, how do we relate a bigger change in momentum to an increase in pressure? Increased temperature means increased mean kinetic energy. Perfect. Meaning momentum of the particle increases. Good job. Oh, but the pressure is not staying constant here to my face. Remember, what we're doing is we're keeping the volume constant. We're trying to see how pressure and temperature are related so they can change. So when we're looking at how two things are related, the pressure and the temperature can change. It's the volume this time we're staying constant. Yeah, we talk about force, right? So we know force is change in momentum over time. Because we're keeping the volume the same, right? It's the same container, the same volume. The time between collisions is not, we're not changing the volume. So we've increased the momentum, so what must happen to the force? So if we increase the momentum, this one's quite nice. You just have to say the force gets increased. And then we know that because pressure is force per unit area, that's how we know the pressure gets increased. Yeah, nice. Yeah, nice, Timothy, sorry. Must increase. Yeah. Temperature increases mean kinetic energy increases, means there's momentum increase. Because the volume stays the same, the force increases, hence increase. Kai, that is like a perfect AQA answer. Like you're talking 3 marks there. That's perfect. Yes, perfect. Good job. Okay, so what we're saying is pressure and temperature are directly proportional. So pressure equals some constant times temperature. Yeah. So it's like someone wrote there in the chat a second ago. Yeah, Carl, good job. It's going to be a straight line for the origin only if the temperature is measured in Kelvin. Yeah, nice. Okay, so that's the pressure law. Okay, so really quickly, whose law is this picture from then? So we just done 3 laws. Just put them up so you remember them. We did Boyle's law, B-O-Y-L-E-S. We did, gosh, sorry, that's shocking. We did Boyle's law. We did Charles' law. And we did the pressure law. So which one is this law? Yeah, fab. Fab, easy. Good job, Timothy. Good job, Cordy. Good job, Carla. Good job, Omar. Yeah, brilliant, right? So the way I do it, okay, because it's, I know we just learned it, so it might be fresh in your mind. The way I remember it, Boyle's law, I think about boiling, but because it's spelt wrong, it's actually got nothing to do with temperature. So it must be do with the other one, pressure and volume. The pressure's got the word pressure in it, so it has to do with pressure. It can't be pressure and volume because I've already used up pressure and volume. So pressure law must be due with pressure and temperature. So Charles' law can't be due with pressure. I've already used it twice. So Charles' law must be due with volume, and it can't be pressure with volume because I've already used it here. So it must be volume temperature. So here, because I'm relating volume and temperature, that's why it has to be Charles' law. Yeah, perfect. Nice. And then we say that they're directly proportional if it's measured in Kelvin. Okay, next one. Whose law is this? Is it Boyle's law, Charles' law, or pressure law? Boyle's law, Charles' law, or pressure law? Oh, we got a mix. Oh, no, we're going for Boyle's. Boyle's. Yeah, Priscilla, good. Carl, good. Isra, good. Yeah, nice. You guys got this. Yeah, good job. So we'll go for it by order again. Boyle's law, I think about boiling. So I think about temperature, but it's spelt wrong. So it's got nothing to do with temperature. So it must be pressure and volume. And the graph is pressure and volume. So clearly, this is Boyle's law. Yeah, nice. Good job. Yeah, brilliant. Easy. Okay, this isn't a common answer that I've had in schools before. Can you read it and tell me why they lost 2 marks? So normally it's like a 3-mark question. So even though they've got really good physics, this is how Pacific AQA is, right? They're not going to get full marks here. So there's always things, you've probably seen it in AQA in year 12. There's things in bold, they underline in the mark schemes, and if they're not in your answers, you ain't getting the marks, okay? It's not as specific for the other exam boards. But again, if you learn it as AQA teaches it, you'll never not get your marks in the other exam boards. Yeah, Kai, perfect. Good spot. Nice. So it says as temperature increases, the particles have more kinetic energy. Yeah, we've lost a mark because we've forgotten here. We're not showing the examiner that we know it's a Boltzmann distribution. We have to say it's the mean kinetic energy increases. Because remember, the particles don't have all one energy. The particles have a Boltzmann distribution of energies. Yes, Israf, thank you. Good job. And we cannot say that they are directly proportional if it's in Celsius. So it says pressure and temperature in degrees Celsius are directly proportional. They're not. Because remember we said if we put pressure against temperature in degrees Celsius, it crosses the graph at -273. So they're not, that's not a directly proportional relationship. That's a linear relationship. So it's only directly proportional if it is in Kelvin. Okay, so just always be careful about that. It's only directly proportional is in Kelvin. This here is a common multiple choice question. So you know at the end of your papers, you got all those multiple choice questions. This one's a common multiple choice question where they ask you, how would the graph be different if it was in degrees C or Kelvin? Okay. Yeah, nice link with impulse. Yes. Okay, next thing we have to do, if you do chemistry, so I know a lot of people do physics and chemistry, you're probably very happy at this bit. But again, I told you this last day, I taught 2 chemists last year and they actually struggled, I think, a little bit more with this because you get taught it differently sometimes. It's annoying though if you didn't do chemistry because you have to learn these 2 equations. So it's not very often in physics you have to learn equations. These are not on your data sheet, but you have to know them, okay? So again, these 2 are not on your data sheet, which is really weird. I don't know why, because every other equation is there. They're not, okay? So I'm just going to talk about these. If you've done chemistry, they're going to be easy as. If you remember your GCSE chemistry, they're going to be easy as, but if not, they're going to be a bit of a struggle. Okay, so we're going to look at this one first. Okay, so what it says here is if we've got all these balloons here, this is what Avogadro was a scientist, right? So this is what he discovered. He said if all balloons have the same volume, they're always going to have the same number of molecules inside them if they're always at the same temperature and pressure. So for example, if I have all these balloons here, they're all in the same room, at the same temperature, and they're all at the same pressure, every single balloon is going to have the same number of molecules inside it. So the same, if it's all oxygen inside it, there's going to be 1, 2, 3, 4, 5. If it's all neon inside it, there's going to be 5. If it's all water, there's going to be 5. There's always 5 molecules inside it. So what he found out then is that number of molecules is not actually 5. It's actually 6.02 times 10 to the power 23 particles. So he found that if a balloon was at room temperature at the pressure of atmospheric pressure, all balloons or all objects have that same volume of particles inside it. I just couldn't get that many drawn inside a balloon. So he said that number is really large to work with all the time. So the same thing like you learned about electron volts probably in year 12. So remember, instead of saying that the charge is 1.6 times 10 to the negative 19 all the time, we can just use 1 electron volt. So it's just a reference, okay? So he said instead of always saying this number, we can just call it Avogadro's constant, okay? So Avogadro's constant means that number of particles all the time, okay? So you've done it in GCSE. In GCSE, you learned this one, right? So in GCSE, you actually learned both in GCSE. So in GCSE, you probably learned little n is number of moles equals whatever mass we have. And then because it's a chemistry one, that's always in grams, divided by its relative molecular mass. So let's say, for example, we're looking at oxygen. Oxygen is 16.8. So the relative molecular mass there is 16. Or we're looking at nitrogen, 14.7. The relative molecular mass there is the 14. Okay, so that's how we can calculate the number of moles. Or if I told you how many particles there are inside the balloon, you can just divide it by Avogadro's constant, and that's another way to get the number of moles. Okay, Avogadro's constant is given to you in your data sheet, and they'll always tell you what the relative molecular mass is. I just remember these because you do them all the time. Okay. Mass is Mr. Moles. Zila, thank you for adding that. Mass is Mr. Moles. Mass is Mr. Moles. That's nice. Okay, the reason you know these is because you do get these two in your data sheet, and that's what we're going to practice using now. So in your data sheet, you get told that pressure times volume is equal to the number of particles there are in total times K, which is the Boltzmann constant, which is given to you in your data sheet, times whatever temperature it's at in Kelvin. Okay, so remember star has to be in Kelvin. Or you can use this equation, which is on your data sheet. Pressure times volume equals number of moles times R, which is the molar gas constant, which is always just going to be 8.31, times the temperature, which has to be in Kelvin. Okay, so these two equations are given to you, but see how this one's a capital N, this one's a little n. You have to figure out sometimes which one to use, which is why you need to memorize these ones from GCSE. Okay? Okay, so before we practice it, I just want to make sure we're okay with what an ideal gas is, right? Because we talked loads about ideal gases. We talked about Boyle's law, Charles' law, the pressure law. They're all to do with ideal gases, okay? So another question that comes up quite a lot, I know it's quite heavy in the theory today, but we are going to practice it. K, sorry, is the Boltzmann constant. So the Boltzmann constant is on your data sheet. I think it's, I want to say it's 8.85 times 10 to the negative 12, but honestly, that number could have just came from nowhere. Okay, so K is the Boltzmann constant. Okay, so ideal gases all obey these laws, all 5. In exam papers, because I know it's annoying sometimes to talk about exams all the time, but that's what we care about right? In exam papers, they will always ask you for either state one rule or one law or one behavior of all ideal gases. But I've seen one past paper they asked you to state 3. Okay, so you need to know minimum 3. Never asked for all 5, never before. The maximum I've ever seen them ask for is 3. Yeah, 1.38 times 10 to 23. What number was I talking about? What is 8.85 times? I'm going to have to look that up now in a minute. Okay, so, sorry, thanks, Yasir. So again, you don't need all 5, but there's been a past paper question where I asked you to state 3 before, okay? The 3 that I've always learned about ideal gases is I've learned that the collisions are elastic. I think that's a really easy one to learn, number 4. Because you know elastic collisions is when kinetic energy is conserved. Okay, so it's quite a quick sentence to write down. So one behavior that all ideal gases follow, or one property of all ideal gases, it's that all collisions are elastic. Second one I would learn is that the molecules have negligible volume compared to the volume of the gas. Thank you, Garrick. Thanks. Thanks, Ethan, as well. So another one to learn is that the volume of the particles is negligible. What it means is we're not going to try to calculate the volume of an oxygen particle because it doesn't matter compared to the volume of the whole room, right? So the volume of the particle is negligible compared to the volume of the room or volume of the container. And another one that I think is easy to learn is that they exert no forces on each other. So there's no intermolecular forces between them, okay? The other two are fine to use as well. So it just depends which one do you like to use better. Okay, those three I think are the best ones to learn. So again, these are the properties that all ideal gases follow, and only if they're ideal gas laws, only if it's an ideal gas, can you use the two equations that we just saw on the other sheet. So PV equals nRT or PV equals nKT. Okay, so it's the only time you can use those equations if we're told it's an ideal gas, and it only is an ideal gas if it has these 5 properties, and you have to learn 3 of them. Okay. Okay, so just really quickly now, so we can get a bit of break of me talking and a bit of you practicing. Can you tell me what A, B, and C are? What is the 3 names of those laws? Which one is Charles, which one is Boyle's, and which one is the pressure? So just pop in the chat. Can you put some of these in the explain some assumptions you've made in the model? Yeah. Oh, hi. That is because it's a derived. So there's only one time in physics you have to prove an equation. So in physics, you're going to get asked to prove this equation, but it's quite heavy on the math, and it'll probably take us, for my classes anyway, it takes a full lesson just to go through the math to prove the equation. You prove the equation using these laws. So if you do the full course, we will spend a full lesson just proving this equation, but it does take quite a bit of time, so I didn't want to waste a summer school lesson on it. But yeah, we do talk about, and you talk about it in school as well, how we use these to prove that equation. Okay, A is Boyle's law is what I'm seeing. C is Charles' law is what I'm seeing. And I'm seeing, oh no, we're mixed. B is pressure. I think this is the highest vote. But I'm seeing a mix here. Boyle's, pressure, Charles. Okay. So the way, again, I haven't learned this off. I just always think about Boyle's. So Boyle's law, I think about boiling, but it's spelt wrong. So it's actually nothing to do with temperature. Boyle's law is to do with pressure and volume. So the one to do with pressure and volume is this one. So yep, happy days, good job. That's Boyle's law. Pressure law must be do with pressure then. So yep, good job. And then the last one left must be Charles' law. Yeah, nice. Okay, next one then is just practicing you guys using these equations. Okay, so I've given you all the information you need. Okay, so there is Na, that's Avogadro's constant. And can you do the first one then, please? How many molecules are in 0.15 moles of oxygen 16 gas? And again, who here does chemistry? Can you tell us a hint before we start about what's important to remember about oxygen gas? Anyone help us out before we start doing the math? What's important to remember about oxygen 16 gas? Yeah, thank you. Yes, here it's diatomic. Okay, so you need to remember it's diatomic before you start this. So it's O2. So how many molecules are there in 0.15 moles of oxygen 16 gas? So how many molecules? I want to know the number of molecules. So I want to know what capital N is. So see if you can calculate out. So again, just pop in the chat once you get it. But to find out the number of molecules, I just have to do number of moles multiplied by Avogadro's constant. You need to note for the next question, number 2, sorry. So number of moles, 0.14, can't read, 15, multiplied by 6.02 times 10 to the power 23, that I didn't do earlier. Timothy said it's 1.8 times 10 to the power 23. So does I see 555, so I'm guessing that's right. 6.02 times 10 to the power 23, multiplied by 0.15. Gives us, everyone got 6.02 times 10 to the power 23, multiply 0.15. I got a different number. I got 9.03. Did not get me? 9.03 times 10 to the power 22. That's the number of molecules. Multiplied by 2, that's the next one. Are you on question 2? So that's our number of molecules, but then the number of atoms is, remember, one molecule of oxygen is O2. So like you said, it's diatomic. So yeah, for question 2, you multiply the number by 2. Ah, yes, I'm with you now. For question 2, that's the number of atoms is 1.806 times 10 to the power 23 is the number of atoms. Yeah, good job. Right, I'm with you now. Yeah. Yeah, I was like, oh, I tried it in my calculator 3 times there because I was like, why am I getting different answers? Yeah, good job. So what we're saying for number 1 there is the number of particles is number of moles times Avogadro's constant. We were told the number of moles, we multiplied by Avogadro's constant, and we found out how many molecules there were. But then the next question was just to see if you remembered it was diatomic. So I asked for hints. So that's how many molecules we have, but a molecule is made of 2 particles because it's diatomic. So that's why we multiplied it by 2 to figure out how many atoms are present. Nice. Okay, question 3. What do you think? So question 3 says, carbon-12, this is the mass of a molar mass. How many atoms are there if there's 50 grams of carbon? Pop in the chat. How many grams are there if there's 50 grams of carbon? How many atoms are there is there 50 grams of carbon? Okay, so what they're telling you here is that the mass of 1 mole, so I know 0.012 kilograms is the mass of 1 mole, but I've got 50 grams of carbon. So your first thing you probably want to figure out is how many moles that is. So how many moles is that? And then I want to know how many atoms is that? Yeah, Kai, this is exactly what I got. The Bilia Canini is brilliant too. Yeah, good job. Omar, straight on it as well. Nice. Good job. So what I would look at here is that's kilograms, right? So what that's really saying is that 12 grams is 1 mole. So then I have to multiply that number up. So I multiply this number up by the same thing to get the 4.17 moles. So I know how many moles I have. To get the number of particles, I just have to multiply my number of moles by Avogadro's constant to get a final answer of 2.51 times 10 to the power 24 particles. Yeah. Okay. Bish, bash, bosh. Easy. Nice. Okay. Moving on. Okay. So again, we're just going to quickly look at this one so we can practice it. So this one is just me reminding you that volume is always in meter cubed. That's our SI unit. We know that. Temperature, we talked about a lot, has to be in Kelvin. K, the Boltzmann constant, is not 1.38 times to the power 10. Sorry, I must have copied that in wrong. 1.38 times 10 to the power of, was it negative 12, wasn't it? Sorry, negative 12. Then we've got PV equals nRT. R is just 8.31. So I quite like using this one because you just have to plug in 8.31. And then number of moles, and T has to be in Kelvin all the time. Okay. Okay, so to practice it, can you give this one a go? Y times by Avogadro's constant. What do you mean? How to figure out the number of particles? Because 1 mole of particles always has 6.02 times to the power 23 particles in it. So if I have like 4.1, oh, you mean the last question? Because I didn't ask you how many moles there was. I asked you how many atoms there are. Do you see that there? So the question didn't say how many moles there are. It says how many atoms are present. So that's why once you figured out how many moles there was, to figure out the number of atoms, you had to multiply the number of moles by Avogadro's constant. Sorry, Carla, missed your question there. Okay, so can you have a go at this one then? So all of your equations are over here and all the information you need is over here. So you shouldn't have to go to your data sheet. So it says, calculate the number of moles and the mass. So I want you to tell me how many moles there are, and I want you to tell me what the mass is of air in a balloon. So I know the temperature is 17 degrees Celsius. I know the pressure is 160 kilopascals. I know the volume is 0.00084. Okay, so can you figure out the number of moles and the mass? Give it a go. So what's the number of moles and what's the mass? So hopefully the first thing you're thinking is we can't use degrees Celsius. So the first thing you're thinking is I have to convert that into Kelvin. And I get 290. So that's what we're using for temperature. Hopefully you're thinking that's a kilopascal. So what that is 160 times 10 to the power of 3. That's the number I'm really using for pressure. I was given the volume. And I would probably use PV equals nRT first to figure out how many moles there are. That's one I would like. Yeah, good job. I got 558. Yeah, I see 555. Yep, 56. 56 better. Yep, good job. Exactly. So see now figure out the mass. Moles is not 0.035. So the moles you should get is I got 0.0558 or 0.56. Oh wait, I see 555. Did you mean 0.056? Sorry, I had a wee bit of a blip there. I see 555. Are you sure you meant 0.055 or 0.56? Both are quite different there. Yeah, I see 55. Perfect. Yeah, good job. So what I would do then is 160 times 10 to the power of 3 times by 0.00084 equals number of moles that I want to know times 8.31 times by 290. And when you solve that, you should get number of moles is 0.0558. For the mass, oh, I got a bit different. So for the mass, this is the molar mass. Remember, what's that saying is 0.029 kilograms is the mass of 1 mole. And I have 0.0558 moles. So how do you figure out the mass there? 1.16 times 10 to the negative 3 is exactly what I got, Omar. Yeah, fab, good job. 1.1617. I got 1.62 times 10 to the negative 3 kilograms. Did I do my math wrong there? 1 divided by 0.0558. You do 0.029 divided by the same answer. Yeah, I got 1.62. Yep, Ishak, same as you. I got same as you. Yep, 1.6 times to the negative 3. And then just check if you, actually, Ishak, just careful. It's not, that wouldn't be your answer in grams. That'd be your answer in kilograms. It would just be 1.6 if it was grams. Yep, yes, here. Yep. If it's in kilograms, yep, good job. So yeah, is everyone okay that this is our answer because it gave us in kilograms per mole? That's my answer in kilograms. So it's 1.62 times 10 to the negative 3 kilograms. The number of significant figures? No. The only time significant figures matters is if they actually say beneath it, quote your answer to the correct number of significant figures, which they never do. So in paper 1, so if you're doing AQA, in paper 1 and paper 2, significant figures only matter if they say, quote, the same number of significant figures. I would just say, rule of thumb, for paper 1 and paper 2, you just always give 2 decimal places, like always. Just a rule of thumb, right? However, in paper 3, which is the practical paper, that's the only time it does matter. So paper 3, the practical paper, it does matter how you write significant figures, but not in paper 1 and paper 2. Just write it to 2 decimal places unless it says specifically in the question. Isaac, physics, Bloomin abuses this. I don't know what you're talking about. Okay, next one then. How about this one? Okay, so it says, calculate the pressure in a child's helium balloon at 21 degrees Celsius if it can be modeled as a sphere, radius 20 centimeters, and it contains 3 moles of helium gas. So the whole point here is we want to find the pressure. Isaac, physics, Blooming abuses this. What is it like? Is it like a significant figures? Is it like a way to remember significant figures? I don't know. Okay, so have a go and then pop it in the chat once you figure out the pressure. So hopefully everyone sees number of moles there is 3. Hopefully we're seeing temperature is 21 degrees Celsius. Hopefully we're seeing that we've got a sphere. So it's specifies, I'd probably just draw a little sphere. And I know its radius is 20 centimeters. So I probably write radius is 20 times 10 to the negative 2 meters. And 21 degrees Celsius straight away. Hopefully we're converting that into Kelvin. And in Kelvin, that should be 294 Kelvin. So I'm given number of moles. So I probably want to use PV equals nRT. I'm trying to figure out P. So I must know V. Number of moles, I know is 3. Times R is 8.31. Times temperature is 294. So you just have to remember how to find volume. 2.2 times 10 to the power 7 is a bit high, Kitan. So hopefully for volume of a sphere, it's on your data sheet at the very front, but it's 4/3 of pi r cubed. Okay, so 4/3 of pi r cubed. So volume is 4/3 of pi times the radius. Remember, it gives us centimeters, so it's 20 times 10 to the -3 all cubed. That's your volume. And when you find that volume, then you should get 0.0335. So that's the number in here, 0.0335. Yeah, Kitan, perfect. Yeah, good job. So yeah, perfect. Exactly what I got. 2.19 is what I got. I just think 2 decimal places is safer, but that is right. 2.2 would get you marks. 2.19 get you all your marks, not just some marks. Pascals, or another way to write pascals, because pressure is force per unit area, is just in Newton per a meter squared. So you can either write pascals or Newton per meter squared. 2.19 to the power of 5. Yes, here. Yep, perfect as well. I see 555 are good too. Yes, good job. Okay, so how are we feeling? These are quite nice, right? So again, it's just kind of like a lot of knowledge, but once you can get the few equations in, they're quite nice again. Explain it again. Yeah, of course you can. Okay, so it says number of moles is 3. It said the temperature was 21 degrees Celsius. So first thing we're thinking, that has to be put into Kelvin. So I added 273. It told me that we're modeling it as a sphere. Okay, and it told me the radius of the sphere. So I know the volume of a sphere, right? Because I need the volume in order to find the pressure. So that's how I knew I need to find the volume of that sphere. And I know the volume of a sphere is this equation. And if you don't remember it, it's okay. It's in the front of your data sheet. So the volume of a sphere is 4/3 of pi r cubed. So I do 4/3 times by pi in my calculator times by the radius cubed. But it can't be in centimeters, which is why I changed it into meters. So centi is times the -2. So when I find the volume there, that was the volume of my balloon. So once I had the volume of the balloon, I just plugged it in here. So I have pressure times volume equals number of moles, which is 3, times R, the molar gas constant, is 8.31, times the temperature in Kelvin, 294. So what I do is you multiply these three numbers together and divide by 0.0335 to get your final number for pressure, which is 2.19 times 10 to the power 5 pascals. Oh, yeah, sorry, I did. Thank you. -2 there. Again, that's just me making a blip, but the math is right for -2. I just wrote it in wrong. Thank you for popping that out to me, Poonan. 4/3 of pi r squared. Yeah. Yeah, well, Timothy, I don't know why I keep trying to give you nicknames. Yeah, so yeah, just be careful that one. I think a lot of people do that. So remember, surface area is 4 pi r squared. Volume is 4/3 of pi r cubed. But you don't really need to remember it is on your data sheet right at the front. Yeah. Okay, sounds like we're good now. Happy? Okay, last one then is just to make sure we're okay. So we have 5 minutes left. Actually, you can pop in the chat for me. Do you want to do this, or do you want to do the question from the last day that we didn't get to? So just quickly pop in the chat. So just write this or last day. So remember last day there was a question about a copper can being dropped in water, and I said that if we finished early, the next day we could go back to it. So you can just pop in the chat what you would like. Do you want to do this or the one from last day? Okay, we're going to do democracy, so whoever wins. I've got 2 for this and 1 for last day. Oh, 2 for 2. I'll give it 20 more seconds and then we're doing the count. 20, 19, 18, 17, 16, 15, 14. It's 3 to 3, 12, 11, 10, 4 to 4, 9, 8, 3, 2, 1. Yes, dear, you got in for my 1, so we're staying with this. Okay, so too late, we're doing the countdown. You're too slow to type in. So, okay, so we're going to say here, pressure of the gas is doubled and the absolute temperature increased by a factor of 3. What effect has this on the internal energy of the gas? So just pop your answer in the chat. If the pressure is doubled and the temperature is multiplied by 3, what's going to happen to the internal energy? Pop in the chat. Do you think that it will be the same? Do you think it'll multiply by 2? What do you think? So we know, so on your data sheet, so I know you don't have data sheet probably in front of you. If you're doing AQA though, you're going to have your data sheet with you 24/7. I have it on my phone, so you know how you can just save a link. But on your phone, it says the kinetic energy of a single molecule is 3/2 kT. So hopefully you can see straight away, if the temperature gets multiplied by 3, straight away that kinetic energy gets multiplied by 3. Okay, so we already know the energy gets multiplied by 3 because the temperature is multiplied by 3. So the other thing we're looking at there on your data sheet, remember just did, it says in your data sheet, pressure times volume is equal to 1/3 of Nm CRMS squared. So we didn't look at this equation, but I just wanted you to try and look at your data sheet a bit. So this looks a lot like 1/2 of mv squared, which is my kinetic energy. It's very similar. So if this side stands for energy, that must mean that this side, P times V, also stands for energy. So if the pressure gets multiplied by 2, the energy must also get multiplied by 2. So if it gets multiplied by 3 and multiplied by 2, it's going to get multiplied by 6. Yeah, these are all on your data sheet. So on your data sheet, it says, maybe I probably should have had that on that slide, sorry. On your data sheet, when you go to this topic, so you know how your data sheet in AQA is split by topics? It says mechanics, it says electricity, it says particle physics. This one's under thermal physics or further mechanics. Sorry, it's under further mechanics, thermal physics. You'll have all the equations there. PV goes in RT, PV goes NKT, and then you have these two. I just wanted to point them out to you that it says kinetic energy of a single particle is 3/2 kT. So if temperature is multiplied by 3, kinetic energy multiplied by 3. Also said in your data sheet, PV is 1/3 of Nm CMS squared. This side stands for energy, so these also have the units of energy. Or you can just double check that with your SI base units. Pressure times volume is your SI base units for energy. So if we double the pressure, we double the energy. Okay? This is Key Stage 3 science. No, but you first learn it. You did this in Key Stage 3? What were you doing? Okay, what about 2 and 3? Can you pop your answer in the chat? Give me your number 2. So your perfect AQA answer using the kinetic theory of gas means, remember we talked about, you have to say about momentum. What's the effect of increasing temperature on the pressure of a gas, and whose law is that? So can you pop your perfect answers in the chat just the last minute there for number 2? So using the kinetic theory of a gas, explain the effect of increasing the temperature on the pressure exerted by a sample of gas. So we'll just finish off with this question, number 2. So just think, you're in your exam right now, you've had this question. What would you type? What would you write to try and get your 3 marks? It is the pressure law, yes, but yeah, good job, pressure law. So I want you to explain the pressure law. So you got 1 mark for telling me it's the pressure law. Because remember, Boyle's law looks like boiling, but it's nothing to do with temperature, so it's volume and pressure. So this one must be pressure law. Good job, Kai. So how are we going to explain the pressure law? So we know it's pressure law. And the pressure law we know is pressure is proportional to temperature. They're directly proportional. So Timothy says if we increase the temperature, it means we're increasing the mean temperature. Did you mean to write temperature twice? EK mean, yeah. Increased temperature means increase the mean kinetic energy. Good job. But since the volume is constant, good job. The volume has to stay constant. Good job. The force increases leading to increased pressure. Yeah, Timothy, perfect. Good job. Carl, increasing the temperature results in increasing the mean kinetic energy. That's your mark there. Perfect. According to the pressure law, an increase in pressure causes an increase in temperature. You've done a really good job of saying it's increasing kinetic energy. But remember, both of you've actually, I just read yours again there, Timothy. Both of you forgot something else. I said it has to be in there. Remember, we've got to talk about momentum. As temperature increases, the mean kinetic energy of the gas increases. Okay. This means that there is a momentum increase. Good job. Because the volume will stay the same. The force increases, hence increase in pressure. Yeah, perfect. Okay, that's like a star. Carla, as temperature increases, there's a higher mean kinetic energy and therefore higher change in momentum. Fab. Because the volume stays the same. Fab. The force increases, so pressure increases. Fab. Good job. Yeah, perfect. So just to go over that. So what we're saying is if temperature increases, what we have to write is that the mean kinetic energy increases. They can write mean to make sure they know that we know it's a Boltzmann distribution. If the mean kinetic energy increases, that means there's a bigger change in momentum. And I'm going to write in my test that force is change momentum over time. So remember to write the equation to show them how you do this. So if there's a bigger change in momentum, but the volume stays the same, so the time doesn't change, that must mean there's a bigger force. I know force is pressure over area. So if there's a bigger force, there's a bigger pressure on a unit area. Yeah, that's fab. Good job. Just because I just saw this question about exam boards. So OCR and AQA have the exact same stuff on the exact same learning, okay? The only difference is OCR aren't as particular about your definitions as AQA. So for AQA especially, so I'll always be teaching the AQA definitions, but if you learn the AQA definitions, you'll never lose marks in OCR. But if you learn the OCR definitions, you would lose marks in AQA, right? So OCR and AQA are actually nearly identical. EdXL as well is basically identical. However, the problem is when you're coming up to your exams. So your exams are quite different. So the only time it really matters what the spec is the month before your exams, because when you're revising just for paper one, you want to make sure that you're revising the right content that's on paper one, because the content on paper one is different from the content on paper one in AQA. So AQA only tests mechanics, electricity, particles and waves on paper one, whereas I can't remember exactly, but I think I'm better at AQA. And OCR, I'm pretty sure waves can come up in either paper one or paper two, if you know what I mean. But if you're deciding between whether doing this course or not because you want to see the cross link between OCR and AQA, if you just send us an email or send me a message on TikTok or on Instagram, I can try to like personalize that message to you a little bit. Yeah. But that's us for today. You guys are great. And thank you for, like, you're really good in chat. So I do hope you guys do the course through the year, because it was quite a nice lesson today. Well, it was nice for me anyway. So I hope it was nice for you guys. But you're free to go. I hope you have a lovely Thursday. Then tomorrow's Friday. And the weather is supposed to be fab this weekend. I don't know if you saw, but it's supposed to hit 30. Pretty sure it was 30 on Sunday. Was it 29 Sunday? You're so welcome. Thank you, Omar. Thank you, IC555. Thank you, Carla. Thank you, Timothy. Thank you, Omar. You too. I'm actually going to do some TikToks right now. So if you're looking for more exam questions, follow us on TikTok. And then remember, just give us feedback as well. So you know how there's Trustpilot. Let us know what you think, what things you like better, don't like better, or let me know personally. Hopefully it's just good, all good, right? Rahina, oh, bye. Sorry, I don't think it's in your name yet. Thanks for saying hi. Bye, guys.